to the equilibrium unit, and the next thing we've learned is Le Chatelier's principle. So we started off with the equilibrium expression, some definitions, moving on to calculating concentrations, ice charts, and now we're into stressing a system. So when we're taking a look at stressing a system, we want to know that there are 3 stresses that you can apply to the system. So you can change a concentration within a system. So this only applies to our gases and aqueous substances that are dissolved in water. So you can either increase or decrease your concentration. The next change you can apply to the system is, there we go, change in temperature. So we know from thermo that we can write energy or enthalpy as part of an equation. So depending on which side you see enthalpy, whether it's endo or exo, you can heat or cool a system, and then it's the same thing. You're either increasing or decreasing, and then you shift accordingly. The other change is a pressure or a volume change, and this only applies to gases. So that is our starting point, that we can stress a system based on these 3 stresses. So when we look at an old diploma question and we have the reaction, and it tells us that within the system you have ice water and then it's this more blue color, or you have hot water and then it's more green, and this picture in here is showing perfect equilibrium. So now when you're looking at a system, you're going to start seeing colors associated. So for instance, if our reaction lays more to the right-hand side, meaning you have, this would be my left-hand side. My left-hand side, meaning you have more reactants than you do products. If you had more reactants than you do products, your solution will be more blue in color. Right now, the rate of the forward and the reverse reactions are still the same. So that's why we're in equilibrium. But then the opposite part is, if we were to have more products, we're going to have more of a yellow color. So we can help figure out if it's endo or exo based on these colors. So I'm not sure right away which one it was. So what I would do is add my energy or my heat to just one side of the equation, and I could have chose my product side, and I want to see if what it says is true. So anytime I add in heat or add in anything, you want to shift away, right? If we're adding in heat, that means we're adding in a reactant. So the equilibrium will shift away, so shift to the right to develop equilibrium, so that reestablish is what I'm trying to say. So this makes sense for what we're seeing in the picture. If you add in heat, so meaning putting your whole system on hot water, you will shift to the right, causing your system to look more of a yellow color. We're not seeing yellow, but we do know that blue and yellow make green, so that would make sense. Now, the opposite to that is if we decreased our heat. If you decrease, you want to shift back to replace it. So that would make us shift to the left, be more blue. So this is definitely endothermic, but you can just double check that with if it was exo. So if I didn't believe it was endo and I put my heat on the product side and then asked myself the same questions, if I was to add in heat, I would shift to the left. I would shift away. So I should see more blue. So when I look at my hot water, it's more green. So that's not true. Then the opposite of that, if I decrease my heat, meaning put it on ice, I want to shift to the right to replace what I'm taking out. And so I should see more of a yellow color, but I don't. I see this blue color. So we know exo is not right. Endo is definitely the answer. Now, my little summary here for when you are looking at Le Chat and you're dealing with shifts, anytime you add in, so for heat or concentration, you shift away. So if you add in reactants, so increase reactants, you shift to the products. So that would be a right-hand shift. If you add in products, so opposite, you shift to the right towards your reactants to make more reactants. Now, the opposite, if you take out, you move back to where you were because you want to replace what you're taking out. So for instance, for reactants, if I decreased it, I would want to shift back towards it to make what I'm taking out. Same thing with products. If I have my reactants going to my products, if I decreased my products, I would want to shift back to it to replace what I'm taking out. And then the last one, pressure and volume changes, that all depends on moles. So what I tell my students is I remember that if I increase my volume, I move to the side with more moles. So this type of equation is definitely, you need that balanced chemical equation, which you would need anyways. And then you see which side has more moles. And then if you're increasing your volume, you would shift to that side. The opposite to that, if you decreased your volume, you would shift to the side with less moles. And if there were the same amount of moles on each side, there is no shifting. Equilibrium stays the same. The last thing I'm just going to add here is just to remember the relationship between pressure and volume. So again, this is what I always remember because I can figure the rest out. So instead, if it didn't ask me about a volume change, but it asked me about a pressure change, I would remember that if my volume is increasing, that would mean my pressure was decreasing. So that would also mean if I decrease my pressure, I move to the side with more moles. The opposite to that, if I'm decreasing my volume, I would be increasing my pressure, so that I would move to the side with less moles. Again, if your moles are the same on each side and there was a pressure or volume change, there is no shifting. And pressure and volume only applies to gases. I hope that helps. If it does, please like and subscribe. And if you have any comments or would like me to do any video, please write that in the comment section. Thanks for watching.